2.5 is a really big step, a really big section of notes, but the nice thing is it's really nothing new except it might remind you a lot of step 18 from Algebra 2. It's all about the rational functions, about all the horizontal and vertical asymptotes, the holes, the intercepts, and finding a way to graph these functions. But hopefully a lot of this will come back and feel very familiar as we go through them. The biggest difference is that we are going to look at the asymptotes more from a calculus perspective using our limits. So, for example, the first one here, find the domain and the equations of any vertical or horizontal asymptote. So I'm just going to talk you through this first example here. The domain, we just zoom in on our denominator to look at the domain of a rational function. So looking right here, that's too big, too much. Let's make that a little smaller there. Okay, here we go. If we just look at our denominator, the denominator cannot be 0, therefore x cannot equal 3. So a way that we could write the domain would be to say from negative infinity to 3, and then again from 3 to infinity. That's how we could state the domain. Or you can just say all real numbers except 3. That's fine too. Okay, asymptotes. Vertical asymptotes happen when we have a domain restriction. So in the past, in Algebra 2, we would just say we have a vertical asymptote of x equals 3. You can also see here, looking at this chart right in here though, as we approach 3 from the left, we're getting closer and closer to negative infinity. And as we approach 3 from the right, 3.1, 3.01, we're getting closer and closer to 3. You can see the numbers are approaching positive infinity. They're getting big in a hurry. 71, 701, 7001. So that's creating that vertical asymptote. That's how we can confirm it using limits. Horizontal asymptotes, we've always compared the degrees of the numerator and the denominator. You can see this is 1 and this is 1. Therefore, the horizontal asymptote would be the ratio of the leading coefficient. In this case, y equals 1. We can compare that with a check our table here and look at what happens as we go, as x gets really, really, really small, negative infinity, we're approaching 1. And as x approaches positive infinity, we're also approaching 1. That's a way that we can confirm that with limits. So this shouldn't seem too new or too foreign to you because we've kind of done that in Algebra 2, but just taking a look at it from a calculus perspective does change things a little bit. Right here you can see that if we look at the denominator again, we don't have any real zeros. So we don't have any restrictions actually. There aren't any real zeros that would cause a problem. So the domain would be all real numbers. And we could state it as such. We could say negative infinity to positive infinity. Consequently, because there aren't any restrictions in the denominator, we don't have any vertical asymptotes. And finally, we can look at the ratio of the leading coefficients because again, 2 and 2, we look at 8 over 4, which is 2. So we're expecting to have that horizontal asymptote at y equals 2. And sure enough, that's what happens. We could also look into a table of values, and you would see that as you go to the left, we approach 2. As you approach infinity, we approach 2. F of x approaches 2, I should say. So that's where we get that horizontal asymptote. All right, so for this one, the domain, let's try pausing the video and see if you can get this on your own. Hopefully that went well for you, and using what we know from Algebra 2, you were able to determine the domain, vertical asymptotes, and horizontal asymptotes. Okay, so again, here it is all written out for you about finding these asymptotes. Vertical asymptotes occur if we have a real zero in the denominator. Horizontal asymptotes can be determined by comparing the degrees. That should all seem pretty familiar. Again, if the degrees are equal, it's the ratio of the leading coefficients. If the degree of the numerator is less than the degree of the denominator, it's going to be y equals 0. If the numerator is greater than the denominator, there is no horizontal asymptote. That's what happened in example B up here. The degree of the numerator was 2 and the degree of the denominator was 1, so there was no horizontal asymptote. Okay, intercepts. We know how to find intercepts. To find an x-intercept, you make y0. To find a y-intercept, you make x0. Not too big of a deal. So let's try this next one. In order to graph a rational function, we're going to practice graphing them now. We want to find the domain, sketch the asymptotes, plot some x and y intercepts, and then a few other points along the way to fill out our graph. Here's an example where the degree of the numerator is less than the degree of the denominator and vice versa. So right here you can see that the degree of our numerator is 0, the degree of the denominator is 1. That means y equals 0 should be a horizontal asymptote for this particular problem. And sure enough, you can see down here, there's our asymptote. We also know that x cannot equal -3, so that's where we get our vertical asymptote. We know there are not going to be any x-intercepts because there's an asymptote on the x-axis. That can't happen. You can't cross it and avoid it at the same time. If x equals 0, if we put a 0 in for x and solve, that would be 6/3, which is 2. So 0, 2 is our intercept right there. You can see our intercept, 0, 2. That's the only intercept. Then we can plug it into Desmos or our calculator, find a few more points to plot. You can see you just got to get it close as you can, and then connect the dots. Not too big of a deal. Another example that I left here in the notes for you. So let's try this next one here. Again, we want to come up with our domain. So we know that x squared plus 2x minus 3 cannot equal 0. We have to factor that to find the x values actually though. So x minus 1 and x plus 3, that means x cannot equal 1 or -3. That means we would have a vertical asymptote at 1 and at -3. And how would we write the domain? We'd say from -infinity to -3. Oops, I forgot the union. Not a huge deal, but want to be consistent, to 1, and again from 1 to infinity. That would be our domain. Okay, horizontal asymptote, we're expecting that there should be 1 at y equals 0 because the degree of the numerator is less than the degree of the denominator. So we're expecting y equals 0. And now we need some points. So if I let x equal 0, that's a 0, that's a 0, I end up with 2 over -3. So that's one intercept. When x is 0, y is -2/3. Again, I can't have any x-intercepts because I have an asymptote there. So 0, -2/3 would be a point here. And from here, we just need to hop on over to Desmos and get a few more points from the graph. Or you could hop over to TI, that would be fine also. Okay, we're typing 2 over x squared plus 2x minus 3. Let me double check that. Yes, that's correct. Okay, you can also then hit the gear wheel, hit the table. You can see a few more points that you could plot. -1, -0.5. 0, we already have that one. Okay, so you kind of get an idea of where this is going to be. We're going to have points right here. And then we also have a branch up here and a branch over here. And we've graphed it. Okay, one thing I want to point out though, sometimes these horizontal asymptotes get a little tricky. And let me show you what I mean. I found this really great source because I thought it would be really helpful. Where did it go? 1 second, I have to find it. All right, it's at this resource, purplemath.com, horizontal asymptotes. Here is something really, really interesting that we didn't explore in Algebra 2, but I love how it lays this out so nicely. Vertical and horizontal asymptotes differ in the following ways. Vertical asymptotes are sacred ground. They must never be touched. Horizontal asymptotes, on the other hand, are useful suggestions. You can never touch a vertical asymptote, but you can and often do touch and even cross a horizontal asymptote. I know, it's kind of mind-blowing. It's like, wait, in Algebra 2, the horizontal ones were sacred ground as well. Yes, that is true. But now we're in Precalculus. We're going to level up and we're going to explore other options. Vertical asymptotes indicate a very specific behavior. Horizontal generally are indicating the behavior as we approach positive and negative infinity off to the sides of the graph. Vertical asymptotes are found by finding the zeros. The horizontal asymptotes you find by comparing the degrees. So, for example here, in this particular case, we expect that there are no vertical asymptotes because there are no real zeros. You can't factor x squared plus 1. We also expect that y equals 0 would give us a horizontal asymptote because the degree of the numerator is 1, the degree of the denominator is 2. However, when you graph this, you'll notice that that doesn't happen. Let me go ahead and toss this into Desmos, x plus 2 over x squared plus 1. All right. So you can see that there is no vertical asymptote. The purple line goes completely left to right. You can also see that y equals 0. In fact, I'm going to put that in here. Y equals 0. We thought there'd be a asymptote there. Look what happens. The purple graph crosses right over that asymptote. Okay? It does function like an asymptote as we go to the right. See how the purple line is slowly approaching the blue line? And as we go to the left, you see how the purple line is getting closer and closer and closer to the blue line, but it never touches it? But in the middle, close to the origin, the graph crosses over that asymptote. That's because we have other terms at play here. These are more complicated rational functions. Having extra terms or constants can have an impact. So just know that it is important to still be aware of that asymptote of y equals 0, but know that the graph can and likely will cross over it from time to time. And you can see here, looking at a graph, that it starts off right here when x is very, very negative. That's pretty close to 0. But right here, it not only gets further from 0, it crosses over, becomes positive, then it kind of comes back down and approaches 0 again. So I just wanted to point that out to you so that it didn't throw you for a loop, because that can be very confusing. You can find yourself saying, what is happening here? Why are these doing this to me? So, all right, going back to our examples in the notes here, graphing a rational function where n equals m. Here are leading coefficients. Degrees are equal, so the leading coefficients are the asymptotes. And this gives you just another example. And I will have you pause your video again and try example 3a and 3b. All right, so here you can see how I found my domains. I also found vertical asymptotes, horizontal asymptotes, looking at the ratio of the leading coefficients, found some intercepts, and then connected those intercepts and a few extra points. Okay, so what happens if we don't have a horizontal asymptote because the degree of the numerator is bigger than the degree of the denominator. Well, in a very specific case, if the degree of the numerator is just one more than the denominator, we get a slant asymptote or an oblique asymptote. And we can find the equation of that diagonal line or that diagonal asymptote by dividing. So you can see right here, we are literally taking 2x cubed, no x squared, no x, and a constant, and we're going to divide it. Oh, can't do it synthetic because it's x squared. We can do it long division style. 2x cubed, no x squared, no x, and a constant. And when we multiply here, we know that x squared would need to be multiplied by a 2x. Gives me 2x cubed plus 2x squared minus 24x. Change your signs. Draw a line and combine. Now I'm going to multiply by negative 2. Negative 2x squared minus 2x plus 24. Change your signs. Draw a line and combine. This is the equation of our oblique asymptote, the line 2x minus 2. So literally on the graph here, we graph the line 2x minus 2. You don't have to worry about the remainder. We just want the quotient without the remainder. That's how you find the equation of that asymptote. It really does a great job because we have two vertical asymptotes here. X cannot equal negative 4 or 3, as you can see from our denominator. And then the rest of the graph fits through it. Now notice, just like the horizontal asymptotes, the graph can cross the oblique asymptote. And it does so right here in the middle. But notice how that oblique asymptote does determine the shape of these other two branches of my graph. It helps get those on as we approach positive and negative infinity. Okay, so on 4a and 4b, go ahead and try to divide to find the equation of that oblique asymptote and see how you do. All right, you'll notice that I used synthetic division because I could, because they were linear divisors, but you could do it long division style as well. Notice that I began at negative 1 and I went up 1, right 1, up 1, right 1 to graph this line. Then on part B, once I divided it out, I knew I had to begin at negative 1 1/4 and go up 1 over 2, up 1 over 2. And that's what I did to get my equation of that asymptote in. Then you can graph each branch of the function. You might remember that sometimes we don't have vertical asymptotes, we have holes. These are removable discontinuities. It happens because there's a factor in the numerator that will cancel out that factor causing the discontinuity in the denominator. For example, right here, if we factor the numerator, x squared minus 4 becomes x minus 2 times x plus 2. Factoring the denominator, we get x minus 4 times x plus 2. The factors of x plus 2 cancel, leaving behind what's left. That means that at x equals negative 2, it is discontinuous, but it's a hole. So we know there's a hole at x equals negative 2. How do we find the y value, though? We dabbled in that in algebra 2, but here's how we find the y value. We're literally going to put negative 2 into the function that's left over. Negative 2 minus 2 is negative 4. Negative 2 minus 4 is negative 6. That reduces to 2/3, which is the y value that we get for that hole. So that's how you determine exactly where the hole is for this particular problem. You can see here that we're following the same basic idea. We know that the function is undefined at -2 and 4 because of the domain restrictions from the denominator. We know that x equals 4 is a vertical asymptote, while x equals -2 is a hole. You can see it graphed right there, -2. There's a hole in the graph. We know that the degree of the numerator and denominator match, so we're expecting there to be a horizontal asymptote at y equals 1/1, or y equals 1. And finally, then we just find a few other points and connect the dots to graph our function. Last one for this video. Go ahead and pause and try examples 5A and 5B. See how you do, and then resume the video. All right, as you can see, I've graphed my holes, I've graphed my vertical asymptotes, horizontal asymptotes, y-intercepts, an x-intercept actually on the second one because it fit on the graph at 3, 0. I didn't even write it down, but we have one at 3, 0. And I found other points from my table, connected the pieces of the branches, and we have graphs.